Assalamualaikum and good day. In this video, I will explain about examples that related the topic, which is magnetostatic. Okay, so we proceed to example 1, which is related to Biot Savart Law. So the question is, consider a semi-infinite filamentary conductor carrying a current of 5 ampere. So we have a conductor that carrying a current of 5 ampere in the positive y direction. So assume that the conductor is a part of a large circuit. So you need to draw the diagram of the conductor. Okay, this is very easy question. So the first one is you need to follow the instruction, draw the conductor on the Cartesian coordinate. So I will draw it. Okay. This is the Cartesian coordinate. This one is to the x-axis. This one is y-axis, z-axis. Okay, so we have conductor along the positive y direction. In the question already mentioned, the conductor is semi-infinite, but it doesn't mention about the length of the conductor. So we assume I will draw it like this. Okay, this is the conductor along the y-axis. Okay. So the current flow 5 ampere. Okay. So we assume that this is semi-infinite conductor. Okay, this is the diagram of the conductor. And then the second question is, find the magnetic flux density of the conductor, which is B. So remember that B is a symbol of magnetic flux density. Magnetic flux density at point P 460 using Biot Savart Law. So we on the Cartesian coordinate, where is the point P? So we mark the point. Okay, this is x, y, z. Okay, so x is 4, we assume it here, 4. 6 is at y axis, this is 6. So 0 is origin. So we assume that P is here. 4, 6, 6, 0. Okay, next, we must know that magnetic flux density B is equal to permeability times H. What is H? H is actually the intensity, magnetic intensity. It's also known as magnetic strength. We assume that the permeability is 4 pi times 10 to the power of negative 7 Henry per meter. Okay, so this is the constant under free space. Okay, so if we refer to the lecture notes, the magnetic field intensity, the equation is H equal to current over 4 pi. Okay, integration of dl cross product R over R cube. Okay, so this is the conductor that relates with the length of the conductor, not the surface and not the volume. Okay, that's why we use this equation. Okay. From the equation given, okay, you already have current, which is 5 ampere. Now you need to find dl, vector r and r. Okay, so how to find the first one? We need to find r, which is distance vector. Okay, so distance vector r is actually travels from conductor to P in Cartesian coordinate. So distance vector is the travel of conductor to point P here. Okay, so this is r, vector of r. Okay, so we need to calculate the distance vector. We already learn about the distance vector in chapter 1, so I hope everyone know about distance vector. Okay, now the conductor will travel to point P. So at x-axis, the conductor is at origin. The conductor is at origin. It stays at the zero of x-axis. Okay, so that's why 4 minus 0. 4 is come from this point. 4 minus 0. Okay, how about y direction? Okay, why 6 minus y? Because 6 is here, y is along the y-axis. Actually, we want to calculate the conductor that along y-axis. Okay, so that's why we put y. And 0 minus 0. 0 minus 0 because of the z at point P is 0. Minus 0 because the conductor is located at z axis 0 origin here. Okay, so not on the top or not on at the bottom. Okay, so simplify the equation. You will get 4ax, direction of x, plus 6 minus y, ay. Okay, this is r, vector r. So now we already have r here. We can find, this is vector r, this is magnitude of r. So how to find the magnitude of r? You can refer to chapter 1 in the given appendix. Okay, r actually is equal to r squared equal to 4 squared. 4 is come from here, plus 6 minus y squared. So if you want to find r only, we just set the 4 squared plus 6 minus y squared. Okay, so you will get the magnitude. Now you already have the r, and then find the dl. We know that dl is differential length of the conductor. So the conductor is along the y-axis. So we consider it as dly. Okay, so dly along the y-axis, if we refer to the table in chapter 1, dly for Cartesian coordinate is dy ay. Solving the cross product. Okay, so now we already have dl, we already have r, at vector r and also magnitude of r. But dl must cross you must cross product dl and r. So dl cross product with r, you can refer to the table given in the appendix. So this is relates with the dl. Okay. This row relates with the vector r. Okay. Okay, if we refer to dl first, okay, dl at ay only have dy. So ay only have dy. So another the direction of x and z is 0. Okay, so if we refer to vector r, okay, this one, direction of ax, you will get 4. Ax is 4. Ay 6 minus y, so put it here, 6 minus y, and no az. Az doesn't exist. So after we solve this equation, you will get negative 4 dy az. This one is for cross product here. So now just substitute all the components of the equations in the equation here. Okay, you already have this one and this one. Okay. Just substitute all the components and you will get like this. Okay. And then I just remove 4. Okay, bring az because az is just the direction, put it in front. So az here. Okay, this integration is towards dy. After we did the integration, we will get this one, this new equation, not equation, new answer. So substitute 0 and infinite number into y. Okay, so this one 6 minus infinite, you will get negative infinite. Same with the denominator, you will get negative infinite. So negative infinite at numerator divided by negative infinite at denominator, you will get 1. So this is 1. Solve this part, you will get 0.83. So after you solve all of this, you will get magnetic field intensity negative 16.71 Az milliweber per meter squared. So back to the question. For this example 1, the question asks you to find the magnetic flux density, which is B. So B is equal to permeability in free space times H. H is this one, magnetic field intensity. Okay, so just multiply permeability in free space with the magnetic intensity, magnetic field intensity, you will get the answer is negative 21 nanotesla.